Yesterday we talked about gravitational fields and electric fields. We defined, in general, a field as a line of influence that surrounds something. A gravitational field was that line of influence that surrounds a mass. An electric field was that line of influence that surrounds an electric charge. We can define it in a different way too. Okay, both definitions are correct, but another definition for a gravitational field, or for specifically for an electric field here, would be the region in which an electric force acts on a charge. Okay, think about that. The region in which an electric force acts on a charge. Okay, the region in which a gravitational force acts on a mass. Look around you right now. There are gravitational fields around you right now. Okay, around you right now is a region in which a gravitational force would act on a mass if there was a mass placed there. So we can think of it in two different ways, kind of in terms of what causes it, the line of influence that surrounds the charge, or we can think of it kind of in terms of what might experience it, that mass or that charge that experiences the force in that region. Both electric fields and gravity fields are both vector fields because they both have direction versus those other fields that we call scalar fields like light and heat and some other things that don't influence in a particular direction. And of course, yesterday we talked about fields and forces, the difference between the two. In order to have a field, all you got to have is a producer, right? That's the whole idea behind creating fields, is to explain what's happening when you only have a producer. To have a force, you got to have a producer to cause the field, but you also have to have something to feel it. Okay, that mass has to be there in the gravitational field, or that charge has to be there in the electric field, in that region that an electric force can act on a charge. Finally, we define the direction of a field as, in two ways, the way that a positive particle would move if placed in the field. We've got an electric field pointing this way. We put a positive particle right there, it would experience a force this way. If we put a negative particle right there, it would experience a force this way. What caused that field? Who cares? Okay, which way would the particles go in that field? Positive would go with it, negative would go against it. Why? Because that's the way we define the direction. Positives go with the field, negatives go against the field. And of course, that means that it's going to be away from positive and toward the negative. Maybe it was a charge over here that caused it. If it was, it would have to be positive, because that's the only thing that would cause a positive particle to go away. Over here, if there was something there, it would have to be negative. So the field also goes away from the positive and toward the negative. Yesterday, I showed you some diagrams for electric fields. Today, I'm going to redraw those diagrams, but I'm going to redraw them a little bit differently. I'm going to draw the pictures today minus a couple of things, and I'm going to ask you to fill in the blanks. So for instance, I've got a charge right here, and I've got an electric field pointing toward that charge. What kind of charge do I have? Christian? Negative. We know that negative charges cause a field, an electric field that's toward that negative charge. Good. Got to be a negative charge. Okay, you can probably figure out what the next one's going to be. What kind of charge is that going to be that causes the field away from it? Positive. If I was to put a positive charge right here, it would move to the left towards the negative. Right here, it would move to the right away from the positive. What about this one? This one's a little bit trickier here. Two charges. Let's say we've got a field that looks like this. Let's draw this. What do you know based on the shape of this electric field? What do you know about these two charges? Mac? Good. They're like charges. If the field lines join up, they have to be unlike charges and therefore a force of attraction. If the field lines don't join, then it's got to be a force of repulsion, and the only thing that causes a force of repulsion is like charges. So we know that they're like charges. Positive or negative though? Both positive, both negative. Yep. Why do you say they're both negative? Good. We know that the field we know that this is a negative charge because the field points toward it. The field must point toward it and all the other field lines as well. Well, if the field lines don't join up, then they must point towards this one as well, which means that one's got to be negative as well. Make sense? What if I changed everything, took away this, took away all the arrows? I won't do that, but took away all the arrows. How would that change things? Which way would the arrows point? They point outwards from this, right? Outwards, outwards, outwards. What kind of charge would this have to be? Max said that they got to be like charges, so this is going to have to be positive, which means the field lines would point outwards there as well. Look, if they point outwards there and don't join up, then they got to point outwards there as well. Okay, another diagram. Let's say we have something that looks like this. Let's draw a positive right there. I want you to label, or at least tell me how to label the field lines and tell me what the other charge is. Tell me what the other charge is first. Is it positive or negative, Jonathan? How do you know it's negative? No gap in the middle, so the field lines join up. If the field lines join up, it's got to be a force of attraction, and if it's a force of attraction, it's got to be opposite charges. So you're right, that does have to be a negative. Now, which way do the field lines point? From the left to the right, or from the right to the left? Dane? Left to right, right to left. So positive, negative, or negative to positive? Towards the left? Yeah. So they're going to point from the positive toward the negative. If I was to put a positive particle right there, where would it go? Would it go toward the positive, away from the positive? Would it go directly toward the negative? Where would it go? Describe its path for me. It would go towards the negative, but not directly. Go ahead. It's going to follow this, right? Okay. It's the direction of the field. If I was to put a negative right there, where would it go? Opposite to the field. So it would follow this path towards the positive particle. Does that make sense? All right, good. We finished off yesterday with a couple equations and one sample problem. The equations that we looked at for gravity, force of gravity, gravitational field caused by a producer, gravitational field experienced by something. This is my force equation. The analogous thing to gravitational force would be electric force. F is equal to K Q1 Q2 over R squared. We won't spend much time on that because we've done that. Yeah, we've done that for a few days actually. The next one is for electric field. And that electric field equation is for when we have information about the producer. In other words, what causes the electric field. Or field in general, I guess. That would be a gravitational field. The electric field would be on the right-hand side. The symbol for the electric field is E with the arrow over it. Why is it important to me that you put the arrow over top of the E? First of all, because it's correct. But more important than writing it down correctly is what, Dom? Yeah, you don't want to get it mixed up with energy. We talk about all those little things that can lead to silly mistakes. Okay, that is a little thing that can lead to silly mistakes. That's a little thing that, in my experience, will lead to a silly mistake. You will make that mistake if you don't put the arrow over top of it. You might still do it. You might still make the mistake by putting the arrow over top of it, but it reduces your chances dramatically because it's a reminder, right, that it's not energy. Equation for this is KQ over R squared. The charge of the producer, the distance from the producer. Finally, the last equation is my field equation for an experiencer. What fields the field? And the electrical equivalent to the gravitational field would be E is equal to F over Q, the force experienced divided by the charge. Now, we did a couple questions yesterday. Any issues with either of those questions? If not, then I want to just take a look at the wording of one or two of these questions. Say number one. We have an ion with a charge of 1.6 times 10 to the minus 19 coulombs. It's placed in an electric field produced by another larger charge. Okay, so if it's placed in an electric field produced by another charge, then this one has to be the experiencer. Okay, there's a producer somewhere. What do we know more about, the producer or the experiencer? I think it's pretty clear in this case we know more about the experiencer, what experiences the field. This charge, 1.6, is placed in a field produced by something else. We don't know what that something else is. So that's going to be an experiencer. We use the experiencer equation. Same deal down here. Okay, this small charged sphere experiences a force where there's an electric field due to another larger charge. The other larger charge is the producer. So this must be a force felt by the experiencer. And of course, the electric field is felt by the experiencer as well. Use the experiencer equation. In contrast to that, let's try another example here on page 549. Determine the field strength at a position P that's this far away from the center of a negative charge, 1.7 times 10 negative 6 coulombs. We want to find the field strength out here. We don't know if there's anything there. Okay, we just know there's a point in space there. It's like saying, what's the gravitational field strength a meter above the Earth? Is there something there to feel it? Maybe. Maybe not. Is there something there to experience this field? Maybe, maybe not. If there is, we don't know anything about it. What's the producer? What's the experiencer here? The producer is that big negative charge, and we don't know if there's an experiencer. Clearly, we know more about the producer if we don't even know if an experiencer exists. So let's use the producer equation here. Let's say E is equal to KQ over R squared, or 8.99 times 10 to the 9 times the charge of the producer divided by 2.2 times 10 to the negative 2 squared. Why, do you want to find out what that is for me? 3.16 times 10 to the 7, and the units for that would be newtons per coulomb. Now, yeah, it could be. Technically, we need a direction here as well, because they didn't ask me for the magnitude of the field, they asked me for the field. Which direction is it? Well, we'd say, with the way that I drew it, it was downwards, right? But I could have easily drawn that point somewhere else, right? Just the same distance away. We would say in this case that it's toward the producer. The electric field is 3.16 times 10 to the 7 toward the producer. And that takes care of the direction wherever I place that point X. Now, here's a rule of thumb. If you're trying to find the field strength a certain distance away from a producer, if you're trying to find the field strength a certain distance away from anything, then that anything is probably going to be a producer. Think of it this way. Okay? If you want to find the influence of me 5 meters away from me, well, then I'm not experiencing it. I can't experience something if I'm 5 meters away from it. I must have caused it. Does that make sense? You want to find the gravitational field strength 100 kilometers above the Earth. Well, the Earth isn't experiencing it. If the point is 100 kilometers above the Earth, it must be causing it. So if you've got a distance away from a charge, then you've got information about the producer. Got that? If you've got information relating to a distance away from the charge, then you've got to have information about the producer, not the experiencer. Let's take a look at page 549, questions 1 and 2, please.